Let us now look at an unsteady continuity problem. Let's assume water enters the tank at inlet 1 with a mass flow rate of 3 kilograms per second. Water then exits the tank at exit 2, proportional to the height of the fluid within the tank, such that our mass flow rate at state 2, m.2, is equal to 0.6 times h, where h is our instantaneous height of the fluid within the tank. If our tank diameter is a constant of 0.5 meters, the density of water is assumed to be 1,000 kilograms per cubic meter, and our tank is assumed initially empty, we want to determine the variation of height of water within the tank as a function of time. If we draw our problem schematically, we have the following. We have water entering at inlet 1 into our tank, and water exiting at 2 through a pipe down below. Initially our height 0, and as a function of time, our height is going to increase until it reaches a steady state value. We want to determine the variation of this height as a function of time. We begin by expressing our continuity equation. Our time rate of change of mass within our control volume is equal to the sum of our mass flows in less our mass flows out. We only have one mass flow into our system and one mass flow out of our system. Thus, we can re-express our continuity equation as dmCv dt is equal to m.1 minus m.2. Now, we know our expression for m.1. This is a constant, and m.2 is going to be a function of our height. What we have to do is express our mass within our tank as a function of time. Our mass within our control volume is simply our density times our volume, where our volume is our cross-sectional area times the height of our fluid level, which is a function of time. If we substitute our expression for our mass within our control volume back into our continuity equation, we have the following. Our time rate of change of our quantity, rho AH, is going to be equal to our mass flow in our system, 3 kilograms per second, less our mass flow out of our system, 0.6 h kilograms per second. Now, if we evaluate the product rule of our first term, recognizing both our density and area are constant, we have rho A dH dt is equal to 3 minus 0.6 h. If we divide by rho A and move 0.6 ht to our left-hand side, i.e. grouping like terms, we have the following. dH dt plus 0.6 over rho AH is equal to 3 per rho A. We recognize this is a first-order linear differential equation with constant coefficients. We're going to use an integrating factor to solve this equation. If we define p of t as our coefficient of h, our integrating factor mu of t is going to be the exponential of the integral of p of t dt, which is equal to the exponential of 0.6 t per rho A. Substituting this back into our differential equation, our ODE becomes the following. The exponential of 0.6 t per rho A times our quantity dH dt plus 0.6 rho A h of t is equal to 3 per rho A, the exponential of 0.6 t per rho A. This first term, we recognize, is a result of our product rule. That is, that term can be expressed as the exponential of 0.6 t per rho A times h of t differentiated. And this is equal to our right-hand side. Now, if we integrate both sides of this equation, we'd have the integral of our left-hand side, which is the exponential of 0.6 t per rho A, h of t prime, integrated with respect to time, is equal to the integral of 3 per rho A, the exponential of 0.6 t per rho A dt. Evaluating this integral, it's an indefinite integral, we see that our left-hand side becomes the exponential of 0.6 t per rho A h plus c1, our integration constant. And our right-hand side becomes 3 per rho A per 0.6, the exponential of 0.6 t per rho A plus c2, another constant of integration. Our rho A's on our right-hand side cancel. 3 per 0.6 gives us a quantity of 5. And if we define C2 less C1 is equal to some constant, our equation now becomes the exponential of 0.6t per rho A, h, is equal to 5 times exponential of 0.6t per rho A plus our constant of integration. Now if we divide by our exponential, h of t is going to be equal to 5 plus c per our exponential of 0.6t per rho A, which is equal to 5 plus c, our constant of integration, times exponential of the negative 0.6t per rho A. And all we have left to do is to solve for our constant of integration by applying our initial condition. When time is equal to 0, the height of our fluid level is equal to 0, and thus we'd have 5 plus c times the quantity, our exponential, of 0.6t, which is now equal to 0, per rho A, which is identically equal to unity, would be equal to 0, our initial condition. That is, c is equal to negative 5. Substituting this back into our expression, our height as a function of time is equal to 5 times the quantity 1 minus the exponential of 0.6t per rho A. At this point in time, you can substitute in values for the density as well as the cross-sectional area of the tank, and you can evaluate this as a function of time.